sorry, 14:10. So you've got
40 minutes, roughly, right?
40 minutes.
That's fine.
And then, how long's your presentation?
Oh,
Do you want time for filling in questions?
I'll be 30 or 35. I'll make sure. I can fit into whatever time we need, so.
Okay. I mean, if we can aim to be, we've already built in 5 minutes for a room to set up. So
Start it here in about
if
3
I
minutes.
sort of just after 2 on that clock, we can think about wrapping up and doing questions. That'd be really good.
Yeah, sure.
Brilliant.
So why don't I let you set up the session for us?
Yep. Just let me know when you're ready.
Hopefully get some help. So, interesting. I very rarely do this in presentations. I believe so, yeah. See, you want to do it? Oh, that works. Okay, cool.
You think we're ready, sir?
Yeah, I think so.
Oh no, some more still coming in. We'll wait. Hi, good afternoon, everyone. We all had a great lunch. Excellent. Right, we've got an action-packed afternoon in the Dome for you. Evan is going to kick off with a session on Docker. So Game of Swans, dances with Docker. So I'm keen to find out what that's all about. 10 past, or quarter past 2, we've got Varun is in here talking about machine learning. We've got a break, and then after the break, the session here at 10 past 3 has been delayed slightly. Dan's asked us to all go into the Waterhouse suite. So 10 past 3 after the break, everyone into the Waterhouse suite for some surprise thing that Dan won't tell us what it is. So we shall all wait, excited to find out what Dan has to bestow upon us. And then 25 past 3, back in here, I'm presenting with Rob and Elisa, session 2 of what we started yesterday. So anybody that came along to our session on building a programmatic telephony application with Asterisk and ARI and Node, we're carrying on today. We're doing conversational apps. So Elisa's going to guide us through how to build conversational apps with the Google Assistant and Dialogflow. And then once that's done in here, we're then going to go into the other room where we thought we were going to have lunch yesterday. And if we have some time, we're going to get our laptops out and actually try and build our own conversational apps with Dialogflow and hopefully plug them into a FreeSwitch and Dractio session that we've got set up. So I'm going to hand over to Evan because I'm already eating into his time. Welcome to Evan.
Thank you. Thanks so much. Stop. Thank you all. Thanks for coming. I know you have a choice of sessions, so I appreciate you choosing this one and coming here and hanging out in the Dome. So what we're going to talk about here is pretty much Docker and Docker Swarm and Kubernetes and orchestration frameworks and how we use that at SignalWire to construct basically a worldwide meta cloud that we can run all of our services on top of. But before I get started on that, I'll tell you a little bit about me. So again, I'm Evan McGee. I'm the CTO and one of the co-founders over at SignalWire. Here's all the normal stuff you can find us at. You might ask, what is SignalWire? Should get us off the bat. So we get that question a lot because we're relatively new, right? We're about a year and a half old. We are effectively an elastic version of software-defined telecommunications. The genesis of the idea behind SignalWire was that Anthony Menesale has been building FreeSwitch for 12 years, along with a number of other people, and Brian West and Michael Jarris, and a lot of other committers from around the world. And we saw a tipping point recently, in the last maybe 2 years, where commodity cloud computing prices, bandwidth prices, the stability of those services, the latency in the cloud, and things like that, came to the point where we realized that you could actually start to build what traditionally we used to put on big iron and hard and high-density machines into very ephemeral cloud instances, and that it actually could be performant, and that you could do it without having to worry constantly about jitter and latency and all the kind of things. We've been tracking this for a long time, and it finally came about that the time was right. And so we decided to create a platform with which to do that, a big scalable elastic cluster of communications tools that can go across the globe and are usable by even the most modest of programmers. A very low-code approach. People don't have to understand SIP. They don't have to understand RTC. They should just be able to take a JavaScript NPM component, put it in, and then instantiate something. And this has been done before. People like TalkBox, and people have done this. It's not a brand new idea. It just we've seen them progress and pivot or do other things, and we find that there might be a better way. So we did that. And we also realized at the time that we wanted to maintain a shepherding of the FreeSwitch project. FreeSwitch being an open source project, traditionally had been shepherded along by whoever was paying Anthony and these guys. Had been Barracuda Networks for a while, Star for a little while. Usually they had to get their salaries somewhere else. Consulting, and I think if you went to David's talk about this, they had to basically be consultants. They had their own consulting firm to help it, but it wasn't enough to really keep the project to the level of what they wanted to grow it. You know, we get to the point where it could be fully tested, and we could actually like have it be rock solid. A lot of the testing for FreeSwitch has historically been things that you would find on bugs. They would release a new master, bugs would be found, they would cut a release, people would find problems. And we all realized the time had come where that needed to stop. We needed to actually have a open source framework that was reliable and consistent. And you know, it's not very sexy, but it's the truth. The future needs to be more stable than the past. So we wanted to build this big global glass of communications infrastructure. And so we started out thinking big, right? We did the exact opposite thing most startups do. We decided we wanted to go big first. And you know, it was a lot of work, and we decided to deploy in all these areas up front. So knowing that up front we wanted to go in Europe, we wanted to go in Asia, we wanted to go in Australia, we wanted to go all over the US, and primarily we're US based, but you know, people everywhere. How were we going to do that? Like, we needed some sort of way to tackle this problem. Could be VMs everywhere, but there's lots of issues we're going to run into. So, you know, what did we choose? Well, first off, we tried to leverage containers. Who here uses Docker in production, or extensively in our case? So most people know about it, right? So the brief overview for those of you who don't know is that really the containerization, the thing I like to talk about with that is, much like a virtual machine, it has a set of resources inside of it. Usually these are very lightweight, very ephemeral, very much like a single process wrapped in a little shell. What you can do, using the Docker images, is create an exact image of what you want deployed. Let's call it FreeSwitch, or let's call it Camellia, or whatever you want. You bake that in with everything you need, configure it through environment variables that are injected when you start the container, and then you can deploy that anywhere that supports the Docker environment. So any virtual machine around the world. And theoretically, if the virtual machines are configured somewhat competently and somewhat identically, as most of them are these days, you can just spin it up and it will just kind of work. It abstracts away that underlying layer. And there are also advantages to packing density, advantages to using web architecture. I mean, a lot of this stuff was built for web architecture, so that is a huge component of what we all do nowadays, right? It's not just the real-time communication services, it's also all the APIs that go along behind it. I mean, we don't live in a world of just sending media around. So you got to think about something that's going to incorporate both your real-time communications architecture, but also the architecture of all of the other web services you're going to need to run your business and do everything else. And that sounds great for one computer, right? So this all runs on one computer. It's all good. Everything can talk to each other. What do you do when you want to run this across hundreds of VMs or thousands of VMs around the world? Well, you're going to need some sort of orchestration framework to do this. And what that is something that can take the individual images and containers and then link them all together. Because on one machine, it's easy. They have a little Linux bridge they all use. They all talk to each other. It's all nice. They have little local DNS and stuff. But you can't go, traditionally Docker doesn't go machine to machine. So you have to basically make it, at this point, there are other choices. You know, I won't get into like Mesos and things like that. I'm going to focus primarily on Docker Swarm or Kubernetes, right? And this is a big debate people get into. I've already had 2 or 3 conversations at this conference about like, which one should I choose? I'm trying to rip apart my entire legacy and I want to choose one. Kubernetes has emerged as probably like the de facto standard of what everyone is coalescing around. However, it is very complicated. You must invest quite a bit of time in understanding it. It is also very powerful. I am here to tell you that if you are getting started now and you want to use an orchestration framework that is lightweight and gets out of the way, I would encourage you to take a look at Docker Swarm, if only because it can get you started in almost 2 lines. And I'll show you actually right now. The real answer is it doesn't matter, right? It doesn't matter which one you choose. You got to choose one of them, go forward, choose something and learn it. And you're going to have a huge learning curve and it's going to be exciting and fun, I think. But just get building and get working. I chose Swarm for these reasons, right? I do think that it's built in Docker Engine, so it just kind of comes, you don't have to install anything else. It just simply scales. It's a very lightweight orchestration layer. It does interbox communication. It does ingress routing. It does all the very basic things. It doesn't do something like shared volumes, right? Some people are like, well, what if I have shared volumes and I want to share them between computers and I have to have like recordings that are between them? Yeah, it doesn't do that. So you solve that by either putting everything into an object store, like an S3, and just assume everything's remote, or if you really need that functionality, you can try to cobble it together with Ceph and things like that, or go look at Kubernetes, which actually has that built in. But understand you're taking a leap in complexity that you may not need up front. Because Swarm has all this stuff built in, and I'm going to guarantee you that for the majority of use cases, it's enough to get you moving, and once you find your pain points, you can solve it. Docker Swarm is nicely upgradable to Kubernetes if you want to. You can actually take the compose files that define them and actually turn those into Helm charts very easily. So don't feel like you're stuck in this. I find it as a nice upgrade path. And here's how you do it, right? I'm not going to walk through this as a demo because I wasn't sure how long it would take, and it always breaks. But this is exactly how you set up a swarm, right? You got to open up these ports. I kind of threw this up here so you can look at it later when the slides go up. These are very simple commands, so everyone kind of knows about them. Open up these ports. This is an important one right here. If you don't see it, the IP protocol for ESP traffic, the encrypted overlay is something I'm going to talk about in a second. And that becomes much more important than you might think. But really, it's two commands. I mean, look at that, right? You have the one command for initting the swarm up top, right? You give it the IP address of the node. It initializes the swarm on that node as a master. You have to have a quorum of masters. You have to have, usually 3, 5, an odd number of them. Make sure you don't have any kind of master contention. And then it gives you a join token. That join token you can literally copy and paste into another VM somewhere. So that one was Los Angeles. This one's in London. Docker Swarm join, it joins. And right there, you do that. You copy that join token to wherever you want, and you're done. That's it. You now have a globe-spanning elastic network with ingress and encrypted communications and everything else. And you can see there's one leader here. There's two, and this is not a very resilient architecture because you only have one master. If that goes down, the whole thing goes kablam. But you have lots of workers. You can have as many worker nodes as you want. You can then tag those worker nodes with things. So a good thing to do from here would be, well, I want to make sure that I run at least one copy of something in London, one copy of one thing in New York. You can tag them as different like resource tags. And then in your description of how you deploy your services, you say, okay, I want to make sure I deploy only to, EU West. We'll call it EU West, right? And EU West must have the following things. It deploys all those. You say, but I want 13 copies. It says, well, how many VMs are tagged to EU West? Make sure there's 13 versions of the service running, and off it goes. Right? And it does all that for you. And it has built-in load spreading and everything else. And you can customize that if you want to, but it also just kind of works off the bat. Some tips and tricks just to make sure that if you do get into this just for fun, things people might not really understand. Like I said before, to have HA, all the masters need a quorum, so make sure that you have enough masters to always maintain a quorum. The masters are pretty susceptible in all of these cases to latency between them because they do a lot of, it's a raft consensus algorithm. If that falls apart, again, things go kablam. And you can recover from it. I've done it. It's not a lot of fun. It's not a good way to spend a night in January. But your services will continue to run. One nice thing is the quorum is lost and the cluster does kind of fall apart. It doesn't mean the services themselves go down. It just means that you can no longer access them or do anything to them, and then things will start to go wonky after a period of time, but there is enough lag here, like a good 5, you can set it 5 to 15 minutes where things will continue while you try to unscrew up the things you screwed up. Going global does mean very high, as we all know, very long ping times across things, very high latency between things. You're going to want to toggle these two things specifically, the dispatcher heartbeat and the node eviction timeout. The dispatcher heartbeat is the thing that tells worker nodes in the swarm that they are no longer consistent and they cannot reach the masters properly. Due to just random networking interruptions in like Singapore or Australia, whatever happens, you will have nodes start to fall apart or fall off the net. As those nodes die, the services will say, well, I was running 5 copies of Camilio down there, and now I'm only running 4, but I have 5 minimum, so it'll try to find another place for them. It'll say you can't find it, services can come back, they can start to be, you're missing some, they kind of get in a weird state. So you want to make sure that if you are doing this as a single swarm that spans the globe, which you can do, you set these timeouts high enough where you can accommodate the latency that will happen with any kind of global service. And the next big thing really is make sure you encrypt your inter-service communication. So let's go back to the whole web services architecture thing, right? Again, you're sending API traffic around. You're doing all kinds of fun things. What you don't want to do is be sending raw, private information around the globe. Imagine you have all of your RTC nodes running in, let's say, DigitalOcean because the bandwidth pricing is better, but you do all of your data analysis inside the GCP. you are going across public interfaces and public internet. You're shipping this stuff, maybe log files, maybe CDRs, shipping across the world. You want to make sure that these things are encrypted. That is traditionally kind of a pain in the butt. You can do it all over HTTPS, which you should be doing sometimes anyway, but then you got to send certs around, you're doing let's encrypt stuff, having to deploy the keys, and it can get fairly complex. One nice thing about both the Swarm it's built in and Kubernetes, they have plugins, is that they can have what are called VXLAN overlay networks. These are virtual networks that are applied to only inside your swarm. So you get like a 192 or a 172 address range. You can actually set it for whatever you want, and you can talk to the individual containers through those. So you basically have an internal one. That is traditionally unencrypted, so anyone can snoop on it. You can just set an option flag to encrypt that. And basically it sets up an IPsec tunnel between all the different VMs, so they all automatically, no matter what, your communications is encrypted. So even if you start to just use HTTP internally for microservices, don't have to worry about deploying SSL everywhere. It just works really well. It does cut your bandwidth by about 30%. So be aware that if you do that, you are doing kind of a big overhead in terms of bandwidth. But again, a lot of the cloud providers, as we'll kind of go through, in terms of their bandwidth availability, it's pretty good, right? Rarely are you pumping, and again, because you're using many small VMs that have a bunch of like very big heavy iron, you're pumping maybe 100 megabits through them at a time. You're not pumping gigabits of traffic through one machine. So it's okay to take that hit, just spawn up more machines to handle it. So again, you have to use any resources available anywhere. So the red ones are the ones that SignalWire is currently deployed, and the blue ones are places we want to deploy into. Because what we want to do is, and I think I forgot the numbers up there, but we want to try to get to somewhere like a 20 to 30 millisecond global footprint, where at any point you're trying to reach our communication services, you're only 20 to 30 milliseconds away from the closest real-time node. And so people who have businesses in Europe would only contact the European ones. They will gracefully fall back to other zones if they're not available, but we want to make sure that people can reach it anywhere. And this is possible now. I mean, the South African one is a great example. Azure just opened up their data center down there, I think in January or February, and we had a cluster there the following day, right? And so we were like, great. And we actually have a customer down there. And we have an employee. I don't know if you know Fred from FreeSwitch. He lives in Uganda. Previously he had to go up to Europe, and now he just goes straight down there. And it's cut down his times by hundreds of milliseconds. So we can do that. Sao Paulo, Australia is a big one. More and more people go to Australia. So we're trying to place them all over the globe in strategic places where people can get fast access, China being a particularly difficult one. And we call these our real-time regions, right? Much like availability zones in AWS or anywhere else, real-time regions are, US East, US West, sort of, and we have North America, like North America South, and South America North and South America South, and then you have just kind of breaking it apart. Each one of these real-time regions needs to be made up of a couple components, right? Each region is made up of a bunch of real-time nodes, so each region has a bunch of different places. US West is currently like Seattle, Los Angeles, San Francisco. It also overlaps with Dallas and Ohio. US East is a much more population-dense area, right? New York City, the whole eastern seaboard is way heavier, so it's Toronto, it's New York, Miami, I think Atlanta. Again, overlaps with Dallas and Ohio. So everything, all the resources inside there can be contained. Each region contains its own local instances of business logic. And what I mean by that is that if you make an API, let's say you're making a phone call from India, and your data is based in the US, you don't want to have an API call transmit back on the call setup or whatever else, all the way back to the US. Some kind of logic happens over here, transmit back to India. You're having about a 1 second just round trip time there, assuming the database isn't contended or anything else is going on. That can't be the case. Those calls have to be fast. Things have to connect. They have to feel snappy and moving. The way to do that is to make sure that you have local copies of things, if at all possible, right? Make sure that you have API layers that exist in those areas. Make sure that the eventing systems, right? If you're taking your events, if you're doing it from FreeSwitch out of ESL or Asterisk pulling out of wherever, and then you need to be able to process those basically in suite in those locations so that as somebody hits a DTMF, again, it doesn't transmit that back to the US, back again, or wherever it's going to go. It has to be able to process that stuff locally and only fall back to data sources as necessary, and as is okay in terms of like when they're playing a prompt and we're waiting for some other resources, do it asynchronously. So point being that we kind of built it all so things would be as snappy as possible in the real-time communications front. And that does mean having to think about where you place all of your business logic and data analysis components. But also remember that no one provider can do everything, right? No one single cloud provider is clever enough or has a large enough footprint to really cover everywhere in the world. So from the beginning, The reason we're using these orchestration frameworks is, like I said, to be very cloud agnostic. You're kind of building your own meta cloud that spans the globe. And once you get to that point, you don't care who you use. Some guys are better at some things, some guys are better at other things. You know, if you use enough of somebody, you get volume discounts. Some people have extra services that are great. Amazon being a good example, but Google also has it. So you start to have to analyze them from more of a business perspective. You become less concerned about their technical capabilities and more concerned about what am I paying for something, where is it located, how can I service my customers? Because what we should be doing is have our communications kind of blending into the background, sort of seamlessly connecting people and doing things. And the infrastructure should take a similar standpoint, in my view. It's a very Star Trek way of thinking about things, but that's kind of my theory. This goes back again to what I was talking about in terms of placing things in certain areas. So what I'm trying to demonstrate with this is that effectively, by choosing different cloud providers, you can optimize for different scenarios. So let's say we have all these guys over here. We're pumping, these are like real-time nodes, little local databases and whatnot. They are all firing, they all have local eventing, right? But all the eventing in SignalWire then passes through the local area, and a lot of the eventing gets passed back to the main cluster for things like fraud analysis and other random things we have to do, right? We use a lot of Kafka, we use a lot of Kafka consumers to pull things off and do different analysis and slice and dice things. But remember, data ingress on a lot of these guys is free. So great, pump as much data down that pipe as you want. Let's say this is GCP down here, and pump it all in there. You do the data processing inside there, and then you just pump out a little tiny stream. You know, the little filtered bits that you need. You might not need gigabytes of all of that raw data stream. You just might just parse, 20, 30K out of it. So you can save a lot of money that way. And as you start to think about that, you're like, oh, okay, I can leverage each one for its own kind of benefit. And it's great. One caveat is that, again, as you're using the public cloud providers, one VM is not like the other ones. Some of them, they have, there can be, if you're using shared ones, they can have resource contention or busy neighbor problems, stuff like that. That has gotten a lot better. So I will tell you right now, this is not nearly as big of a problem as it used to be, and I think we all have been burned by this in the past, maybe. But there is still a bit of a, caveat testor here. Is that next slide? Yeah, caveat tester, right? Testers beware. You got to make sure that you test your VMs when they start up to make sure that they are running okay. If you're starting them up for something specific, like high disk I/O, make sure that they are actually doing the disk I/O they say they will provide. If you're doing things like deploying static services, databases, Kafkas, real-time messaging queues, anything that has a real resource need, those are probably not things you're turning up and down all the time, right? You're probably doing those once a year, twice a year, however you're moving them around. You can just profile those machines and find the best one, right? Sometimes you start up 2 or 3 or 5 of them. Netflix used to spin up 100 machines on AWS and then power down 90% of them and keep the top performing 10%. And then retest them occasionally and just do that over and over again. We don't need to do that anymore because they're all pretty good, but it still is important that if you see something in your metrics, which you should be tracking all these things, if you see something, you should say something and go shut that one down. Remember, these guys are kittens. They're cows, not kittens, right? The traditional idea is that you start up a virtual machine, you name it, call it, Agamemnon, and you're like, oh, Agamemnon's what the database is. You can't touch Agamemnon. Right now, it should just be cow number 1, cow number 2, cow number 3, and poor cows. I don't mean to pick on cows because I love cows, but cow gets gets diseased, and you're like, take it to put it away, and get another cow out. Point being, they should be replaceable and easily mutable. Some things will be special, like databases, but again, hopefully you're architecting your database stuff where it's replicated around, so if one machine goes kind of wonky, you have even multiple standbys, you can be promoted to master, you just kind of off you go, and it moves on. So try to keep that in mind. Go through some of the cloud providers here real fast. This is a quick overview of which ones we use, what we found. So for GCP, we found that GCP is good for disk I/O. They have a very good disk I/O. They also have a very sexy thing where you can attach SSDs to instances and then detach them and reattach them somewhere else, which we found very useful for situations where things aren't performing super well. We can have let's assume we have a massive Postgres database or some sort of database. We can actually turn that one off, promote the standbys, have that all kind of work, power down the original, take its disk, reattach it to a new VM that's more performant, boot that back up again, and then have it resync the data much faster than having to redo 100 or 300 gigs or a terabyte or two. So that's fun. Fun little DevOpsy things like that. They kind of have standard networking pricing across the board, as everyone else does these days, right? Ingress is free, but outbound, they just dropped it, actually. They have 2 different tiers, which is interesting, a premium tier and a standard tier. The standard tier is considerably cheaper. I only use the premium tier. I don't really use the standard tier. I don't really have a reason for that. I have not tested the standard tier effectively. It's just they got me with the marketing. It says premium. we should go test standard, but you can go test it yourselves. It's pretty straightforward. I don't actually give a lot of like network bandwidth analysis in a lot of these slides because we found using them all, they're actually all pretty good. There was like minor variations, but there was some jitter, not very much, very little packet loss, and the throughput was really as rated. They're actually all the cloud providers at this point are pretty solid on that. So GCP is great. I'm actually a big fan of theirs. No big deal. DigitalOcean, another big fan of theirs. Been using their stuff for a long time. They have also a pretty good disk I/O, not quite as good as Google's, but it's actually a little bit more consistent across the board. They have very, very cheap networking, right? And traditionally, the networking was not super duper reliable historically, but they've massively improved that in the past couple years. So you do get, with instances, between 1 to 2 terabytes if included, and it's only a penny per gigabyte, ingress and egress. You're talking, you know, basically an order of magnitude price reduction from GCP if that's something that's important. What do you use that's network intensive? Well, I think we all know what that is. And they have other little services that are S3 compatible for their block storage. It's also a lot cheaper. So again, if you're doing a lot of recording storage or things like that, and you need an S3 compatible store, use them. Azure, again, my favorite thing about them is that they are in many different places around the world. Their disk stuff is pretty garbage. Their networking is just as expensive as everybody else. They do have Windows. If you love Windows, and you can run FreeSwitch on Windows, they have that, so that's great. But, I mean, we have surprisingly had requests for that, and people have asked for that. And so FreeSwitch does build on Windows. It runs on Windows. So, yeah, Azure, Windows, have fun. One thing about Azure, though, is that they are actually quite willing to deal. Like, they're willing to give you pretty great price breaks because they know they are trying to capture market. So if you go to Azure and ask and talk to one of their account managers, push that deal. Like, get your business hat on and be like, you guys got to give me a good, I'm going to go somewhere else. And they're happy to work with you. And they're actually quite pleasant. Microsoft, the new Microsoft is a beautiful Microsoft. Amazon. So, like, by far the worst disk I/O, probably by far the most expensive. They have such a great ecosystem, right? And that's kind of what everybody uses it for. And the people know it, so they like using it. The last one is my little joke there, because most people are like, there was an old saying that I remember that you never got fired for buying Cisco, right? No one ever got fired for buying Cisco. You never get fired for using AWS. No one's going to fire you for making that choice. So people just go to it because it is the de facto standard. I would encourage you, and I have a lot of friends that work at Amazon, and so this is nothing, you know, they're lovely people. I'd encourage you to go elsewhere and look at other things. I think you'll find the other ecosystems to be more welcoming, easier to use, simpler to manage, and to use AWS for what it does really well. S3, Lambda functions, like cool serverless things, all kinds of great stuff they do have. Now, if you're an AWS guru and you know how to like tie it all together, that's wonderful. I don't mean to dissuade you. I'm just saying that you're going to pay for that, so be prepared. A couple other little ones here. Scaleways is ARM primarily. If you're doing a lot of ARM builds, I don't know why you would, but if you have something that's ARM-based, Scaleways has virtual ARM servers that are quite interesting. And Vultr is kind of a newer DigitalOcean. I find them to actually be quite performant as well. And they have very odd data center locations and kind of like more granular ones. So again, for our millisecond footprint, we're looking for providers that have unique locations or multiple locations that aren't just San Francisco and New York. They have like LA and Seattle, so we use them for things like that. But yeah, so again, just to summarize all that kind of stuff, the point of this talk was to say, hey, depending on what you're looking at, look at your services you're trying to build, look at where you're trying to service. If you're only in one country, maybe you don't need a global footprint like this, but dip your toes into the water of these orchestration layers, because really it'll make it so when you do expand, or if you want to expand, you know how to do it. If you are thinking about expanding globally now and you haven't looked at the stuff, give it a try, take a look at these providers. If you have any questions, come find me. I'd love to talk about it. Yeah, so I'm Evan, and thanks for coming, everybody.
Thank you, Evan. Right, open for questions. Does anybody have any questions for Evan?
Thank you. Great talk. Do you have any Docker image on the web that you suggest for FreeSwitch, or any tricks that we should be aware before starting running FreeSwitch on Docker?
Sure. So there is, I think in Tree, there is a Docker file that you can build the image. We don't host one currently, but we will likely do that. Come to ClueCon. Maybe we'll, that'd be a spot where we probably talk about that. And in terms of tips and tricks, so one thing people frequently complain about with Docker and all RTC services is the networking stack, right? Everyone has a problem with the port, because when you open up a port, particularly on Docker, right, it opens an IP table rule. They try to open a large range of RTP ports, like 10,000 through 20,000 or whatever. Each one of those is an individual IP rule in IP tables. and those consume memory, and it just explodes. Like nothing works. You can get around that by using what's called host networking mode, where it actually uses the host networking stack injected into the container, so there's none of that overhead of using IP tables and the masquerading and everything else. That's one way to go about it. There are other ways that you can actually run like Docker inside of Docker, where the Docker container itself has lower level access running Docker that is attached to the Docker socket running on the host. They can then do manipulations inside of that to both allow you to use like the overlay networking along with the host level networking on a certain port range. It's a bit complex and it's kind of enough to go into, but you can use basically like Docker and Docker or host mode are the two ways to really get around that. And those are the big tricks. And people, like you can't do that if you want to if you wanted to put that on your Mac and run it on your Mac that way, because the version of Docker on Macs is hypervisor based, right? It's a hypervisor running on here that's running Docker inside of it. It doesn't work. You can't use host mode on a Mac. So devs on Macs can't do that. It has to be on Linux somewhere, usually somewhere in the cloud. Another good reason why to have your dev and your staging environments be identical to production. One benefit of using the swarm in that way is that you actually can have dev and staging be literally identical to production. You spin up identical resources, it deploys the identical container systems, maybe not scaled quite as far, but definitely like to a point where you can get a good, reliable field test, and you can test out all those things. Yep.
Any other questions? Oh, that came out rather loud. There we go.
Hi, Evan. We are running our production in Swarm like 1 year and a half, and one of the reasons why we choose Swarm versus Kubernetes, it was we were migrating so many from monolithic to microservices, and we didn't want to introduce a big learning curve also with Kubernetes. But I'm finding time to times the old continuous in one worker just shut down.
Like a random worker will shut down.
Yep. So
like an actual node itself will go
yep.
offline.
Yep.
Change the heartbeat. Have you changed the heartbeat?
Nope. Yep. Thank you.
Thank you. Any other questions? Oh, excellent. Well, thank you, Evan.
Thank you all for coming.
Fantastic talk. So next up here, we've got Varun Singh is doing a session on machine learning. His title is too long for me to remember.